Yes.
Yes. Yes.
All right, good morning, everyone. Hope you guys all had a nice break. I have 3 handouts for you guys. So one is the packet that will take us up to the quiz next week. But then the second half of chapter 4, we're going to do after the break, after MLK. Also, your calendar, you guys picked up that, as well as the homework pages for the entire unit. So right now we're only starting with 4.1, 4.2, and 4.6. And then we'll move on to the calculus portions. Okay, so I want to share this real quick here, make sure that everyone. Okay, so we're on chapter 4. This is unit 4 integrals. We can get to it by if you go to calculus on my homepage and go to chapter 4 integrals. At the very top, just like before, are all the homework pages. So if you misplaced your homework pages, you can always grab those from the top of the page. And then CalChat have all the homework solutions. Most of the problems I give you are going to be odd number problems, which you can pull from CalChat. So there's that resource. Also, I worked out problems on my own as well. So if you look on each day, you're going to see selected homework solutions. So if you click on that, some of the problems that I find are more challenging, I would work those out. Sometimes that looks a little bit different than the way that CalChat works it out. So just want to make sure that you guys have all those resources, especially if you're going through your homework and if you're stuck on your homework problems. You have CalChat, and you also have my selected homework solutions for you to look at if you're stuck. Okay. Calendar is also on here, so just want to make sure that you guys know, if you somehow misplace anything that I give out in class, you can pull it from my website. Okay. Okay, so all of first semester has been about derivatives, okay, which is slope related. And if we undo slope, we're going to get something that is area related. And I'll talk a little bit more about, algebraically why that's the case. But, just like with, any math concept that you learn, we always learn that concept and we learn how to undo that process, right? Imagine the first time you learn anything with math is addition, right? You first learn addition, then you learn subtraction. So first semester is all about derivatives, and this semester is about antiderivatives. How do we undo that process? So we're going to start off first with just approximating area under a curve, and we'll move on to the calculus portion next week. Okay, so today's all about setting that stage so that we can do the approximation. But we're going to learn something that feels unrelated, but we're going to see this is going to be a nice tool for us to apply tomorrow and Friday. Okay, so starting off with sigma notation. Okay, so you've seen this before, but we're going to do a full review from the beginning here. So sigma notation is this this E-looking note symbol here, and all that means is that we're going to be adding a bunch of terms together. Adding terms together. That's what that notation means. Okay, so first you have that variable I, that's the index variable. That variable can be anything, but usually I is the variable that you're going to see the most. Okay, we have that lower bound 2. This is going to be the first value that you're going to insert into your rule of sequence. And your rule is this a sub I, whatever is next to the right of that sigma notation. You can call this the formula rule as well. So we're going to be inserting this lower bound into the variable of the rule of sequence. And whatever that gives us, that's going to be the first term. So I'm just going to put a sub 2 to indicate that I plug 2 into the rule of sequence. Whatever that gives us, that's going to be the first term. And then we always increment by 1. So the next term that we plug in is going to be what? 3. Okay. And then we just keep going. 2, 3, 4. And then we stop when we reach the upper bound here. So upper bound is 5 here, this upper bound. Now 5, whatever's up here is going to be the last value that you insert into the variable. Okay. Some students feel like this 5 means that there are 5 terms, but that's not always the case. Okay. It would be the case if it always starts at 1, but that it may not always start at 1. Okay. So if I start at 2 and if I go to 5, there's only going to be 4 terms. So that upper bound doesn't necessarily mean that there are 5 terms. It just means that that's the last value that you insert into the variable and then you stop. All right, so let's practice that process. So we have the lower bound 2, we have the variable I, we have the upper bound 4, we have the rule of sequence, which is I squared plus 1. So we insert 2 in for I, and that's going to be the first term that we're going to get. Okay, so 2 in for I, we get 2 squared plus 1. Okay, we'll do all the addition later. So now that we're done with I equals 2, the next value that we plug in is what? 3, right? Yeah. So plug 3 for I. Keep going. Okay. Do we plug in any term after 4? No, that's the last term, right? That upper bound tells us when to stop. 4 is going to be the last value that we insert in for I. Okay, so then we just add these together. There's 4 plus 1, which is 5. 9 plus 1, which is 10. 16 plus 1, which is 17. 5 plus 10 plus 17. Okay, now if there's only a few terms, it's not so bad, right? You just insert it one by one and add it together. But imagine if we're adding 100 terms or 200 terms. You know, we don't want to go through and we want a more efficient way of adding terms together. So we have these summation formulas that will allow us to have a little bit of a shortcut in certain situations. Okay, so it has to fall under specific rules and it has to fall with the lower bound starting at 1. So we're going to apply or practice using these summation formulas, and we're going to see how these formulas are going to be helpful as we move into Thursday and Friday. Okay, let me just talk about how these formulas work and just convince you that these do produce the correct sum. So the first one is summation from 1 to n. N is the upper bound, whatever the upper bound is, and the rule of sequence is 1. So if I insert 1, I get 1. If I insert 2, I still get 1, right? There's no variable, so it's going to stay 1 all the way through. Let me just kind of show you how this works and convince you that this rule does work. Let's say you want to go from 1 to 5, rule of sequence being 1. Okay, just doing an example here. If I insert my lower bound in for my rule of sequence, I'm going to still stay as 1. Then I plug 2 in, I still get 1. Plug 3 in, I still get 1. Plug 4 in, plug 5 in, and I stop at 5. I add those together, what do I get? 5. Right? And this matches the upper bound, and that's what the rule of sequence says. It says that if my rule of sequence is just 1, whatever my upper bound is, it's going to be the same as my value, because I'm just adding a bunch of 1s together. The second one here says summation from 1 to n, and my rule of sequence is I. So that means if I plug in 1, I get 1. If I plug in 2, I get 2, 3, 4, all the way up to n. I can add those together, but it's a lot faster, especially if there's a lot of terms to go through this formula. So I want to first show you that, convince you that this rule does work. So again, let's say I want to go from 1 to 5. Summation I. So if I plug 1 in, I get 1 plus next term up is 2. We always increment by 1, and we just always keep going until we reach the upper bound. Plus 2, plus 3, plus 4, and then we stop at 5. If I add those together, I get 3 plus 3 is 6, 6 plus 4 is 10, 10 plus 5 is 8. Right, so now let's see if we can apply the rule to see that it will also produce 15 if I were to go through this rule. So the rule says n times n plus 1 over 2. What's my n value here? 5 upper bound, right? So 5 times 5 plus 1 all over 2. 5 times 6 is what? 30. 30 divided by 2 is 15. So I want to first prove you that this rule works. And then you can imagine this is going to be a lot better and faster, especially if we have like 100 terms or 200 terms, right? Rather than having to add up all the terms, this is going to help us get to that sum a lot faster. Okay, so let's just try to get used to some of these problems. A lot of times we have to do a little bit of cleanup work before we can use these summation formulas. Now, on your homework, you're going to see some problems where it's not going to start at 1. If it's not going to start at 1, I think, well, the problem is going to expect you to just do it 1 by 1, to just insert the values. And usually those problems that you see in the homework that ask you to do it manually, there's not going to be a lot of terms. You can do it without too much trouble. But especially if we have, 10 or 20 or 30 terms and it starts at 1, we really want to try to fit into the summation formula so that we can apply these rules and get to our answer faster. Okay, so let's look at example 2. And summation from 1 to 8 of 3i squared plus 2. Now, if you look at this right here, this is a little too much. Doesn't fit into any of these rules exactly, right? So what that tells us is what we can do, however, is we can split this into smaller portions, into separate problems, and we can handle the sums separately. Okay, so the summation is going to apply to both these terms. So I want to just kind of separate them individually, break this individual problem into smaller portions. And this 2 is not just a 2, okay? It's a summation of 2, so it has its own rule. Oh, I forgot to go through this, sorry, I just want to kind of go back and recap. There's also a rule for I squared. It's a little bit more complicated. There's also a rule for I cubed, a little bit more complicated. And then this last rule just says, if I have any coefficient, I can just drag that coefficient in front and then just do the sum and then multiply the coefficient through later. Okay, so I can really kind of separate it as something that's outside of my rule. Okay, so now that I've separated this into two sums, I want to fit these into the rules that I have available. I'm going to kind of move some coefficients around. I'm going to pull the 3 out in front. And now I can see where my rule is going to apply. That 3 is just going to hang out in front until I resolve this portion. And then I can multiply that 3 through. And then the 2, same thing, right? I don't see a rule for 2. So what I like to do is I like to pull that 2 out in front. And what do you think I can put here to make it the same thing as, yep, that's right, put a 1 here. If I put a 1 here, then I can match the rule that I want to use, right? Summation 1. Okay, so I'm just rearranging it so that I can isolate the rule that I want to apply. Any questions? Okay, so now we're going to apply the rule. Summation from 1 to 8 of I squared. I have a rule for that, which is n times n plus 1 times 2n plus 1 all over 6. What's the n value for this sequence here? 8, yeah. So I'm going to say 8 times 8 plus 1 times 2n plus 1. So that's just going to be 2 times 8, which is 16. 16 plus 1 is 17. All over 6. With a times 3 in front, right? That 3 is just going to multiply through my term. Plus, sorry, I forgot to put a plus here. 2 times, and then summation from 1 to 8 of 1. This is, what's the rule for this? Just what? 8, right? Yep, that 8 is going to be my upper bound. I'm just adding a bunch of 1s together until I get to 8, until I add 8 1s together, and that's just going to be equal to 8. So 2 times 8. Okay, so now the rest is just using the calculator to sum it together, right? So 8 times 9 times 17 all over 6 times 3. Gonna jump to the answer here. So that's 612 plus 16. Okay, don't worry about the fact that these are big numbers here. It's the process that's more important. Okay. Okay, any questions with 2? Okay, look, if you look at example 3, this looks a little more complicated here. Got an I plus 2 squared. This kind of looks like I squared, but it kind of doesn't as well because that plus 2. What do you think we should do before we can identify each of the rules that we want to apply? Because these are separate terms, right? We can just separate them, but this is not quite separated. So what can we do to get them separated? Yeah, let's expand it, right? If we expand it, we get the individual terms without the parentheses, and then we can just individualize each term. We're going to spend some time working on this I plus 2. The middle terms can combine. We can make that 4i. So we have 3 terms. You got I squared, you got 4i, you got 4. So I'm sorry, I equals 1 on the left. Okay, to make it easier for me to identify the rule, I'm going to pull the coefficient that doesn't quite match with my rule. Pull it out in front. I'll make this 4 summation I. I'll make this 4 summation 1. So now I have the rules on above that I can apply. Summation I squared, I can use n times n plus 1 times 2n plus 1 all over 6. My n value here is 10. Here, summation I is just n times n plus 1 all over 2 with a 4 in front. And summation 1 is just n, which is 10 times 4. See if you guys can set that up, and then I'll do the math for us. My n value is 10 for all these terms, right? N times n plus 1 times 2n plus 1 all over 6. N times n plus 1 all over 2. And the n and the coefficient just kind of hangs out in front, multiplies with the resulting summation. So really, I'm just applying the rules for these pieces, and the 4s are just hanging out in front until I've resolved it. Ends up being 385 plus 220 plus 40 equals 645. Okay, any questions with 3? Okay, let's look at number 4. Okay, does anybody still need to look at 3? All right, 4 looks a little different. What's different about number 4? Yeah, my upper bound is no longer a constant, right? It's a variable, but we're still going to apply it the same way. Okay, we're still going to go through the same process. And also, what else looks different? Okay, we're used to seeing index variable I. This is index variable K, but it's the same thing. Okay, just they're defining a different variable, but we're going to do the same process. Now, n looks like a variable, but we're going to treat it as a constant. Okay, this is not going to change. It's the K that's changing. The K is the variable that's going to, increase from 1 to 2 to 3, all the way to n. N is just some number. Could be 10, could be 20, but it's set in stone. Okay, so we're going to treat n as a constant. That's something that I know it's a variable, but we're going to treat it as a constant. So if it's a constant, we're going to treat it the same way that we've done before. Any n that we see, we're going to pull out in front, just like how we did before with a 3 or a 2 or a 4. Okay. It's the k that we're going to try to transform using the rules above. Okay. But first, I'm just going to separate this into 2 terms. That minus allows me to separate into 1 for k squared and 1 for the 1. But I'm just going to show that I'm going to have 2 terms I'm going to worry about here. So I'm just distributing the 1 over n through. I'm separating into 2 summations. But as soon as I do that, I'm going to pull the 1 over n out in front of the summation because I know it's not going to change. It's going to just stay as n. Okay, is everybody okay so far? Just rearranging it so that I can apply the rule from above. Now I see summation k squared, but it's the same thing as summation I squared. It's just a different variable, right? But it's still the same rule. So now I'm going to replace this with n times n plus 1 times 2n plus 1 over 6. But I'm not going to have to change n because this is a variable value that I'm going to stay with the problem. So basically, when I get to the end, my answer is going to be in terms of n. I don't have a specific upper value to insert in. It's going to stay as n. So k squared becomes n times n plus 1 times 2n plus 1 all over 6. Minus 1 over n times, okay, summation 1 becomes what? Just n, yeah. Okay, I'm going to clean up each individual fraction here. the n, these are two separate terms, so I can just look to see what I can reduce here. And the numerator and of the first fraction can be reduced. I'm going to FOIL out the numerator here. So I'm going to get 2n squared plus 3n plus 1 all over 6. And then what does this reduce to be? Just 1. And if I just want to match common denominator, I'm going to just say 6 over 6. We want to get this cleaned up so that I can have it all into one fraction. Now that I have common denominators, I can just merge all the numerators together, right? 2n squared plus 3n plus 1 minus 6. 1 minus 6 is negative 5. Right, so we're taking these steps because we're moving towards the tool that's going to help us tomorrow. Okay, so and tomorrow we're going to see everything in terms of n, and we're going to eventually push n out to infinity. So let's go to the next page and continue to kind of transform these problems, moving towards what is going to be helpful for us tomorrow. Okay, so right now you're just seeing kind of pieces of what we're going to do. We haven't shown you the big picture yet, but we're just kind of practicing these tools, and I'll kind of reveal more of the big picture tomorrow. Okay. Now, what I want to review is limits as n approaches infinity. Think back about how we found horizontal asymptotes. So I'm going to put this at the top of the page. Oh, sorry, thanks. Limits as n approaches infinity. So at the top of the page, let me have us do these two review problems. Okay, so thinking back on limits, if we're approaching infinity, we don't plug in the value, right? We do something with the exponent. So do you guys remember, if we are approaching infinity, we find the what? We find the highest exponents in the numerator and denominator, and then we compare it, right? So do you guys remember, if the denominator has the higher exponent, what is that limit going to become? It's going to be just what? 0. Yeah, because the denominator is growing at a much faster rate than the numerator. Eventually, that fraction is going to get smaller and smaller and smaller until it reaches 0. And here's the other big review item here. Again, approaching infinity, we don't plug anything in. We just go to the numerator and denominator, find the highest exponent, compare it. And if they're the same, then what's our limit going to be? Coefficients, right? So this is going to be just what? 3 over -5. Yeah, -3/5. There's also a third scenario where the exponent in the numerator is higher than the denominator, which will go up to infinity. But for our process, we shouldn't be seeing that. Okay, we should only be seeing denominator higher, or the ratio being the same, or the degrees being the same. Okay. If we run into a problem where the numerator has a higher exponent, that's an indication that we did something wrong along the way. Okay, so we shouldn't see that for this, for what we're doing here with approximations for Riemann sums tomorrow. Okay, any questions here, this process for approaching infinity? Okay, so let's look at example 5. Suppose my sum S of n is given as this expression. Find the limit as n approaching infinity. So I'm going to try to clean this up and then compare the degrees. Let me get all this under one fraction. I'll distribute the n through. Well, let me put it all under one fraction first. Okay, compare degrees. Degrees are the different or same? Same. Therefore, what's my limit going to be? 1/2. Yep. We just look at the coefficients. 1 is in front of n squared in the numerator. 2 is in front of the n squared in the denominator. 1/2. Okay. Example 6 also limit as n approaches infinity. But what's sticking out here? Okay, we have to resolve what? The summation and the I. Okay, so basically we want to get everything in terms of n before we can do our limit process. So let's just ignore that limit notation for now. Get this all cleaned up, identify the summation rule, apply the summation rule, and then once everything's in terms of n, then we can clean everything up and compare degrees. I'm going to merge this together here. What does this become? Multiply that out, we get what? 4i over n squared. Again, we'll treat the n the same way that we do the 4 as coefficients. Okay, so we'll pull that out in front so that we have an easier time identifying the rule that we want to apply. Okay, so everybody see how I did that here? It's I can always split up my fraction into multiple fractions. So 4 over n squared times I, same thing as 4i over n squared. I'm just separating the parts that's not part of the rule. But now I can replace this with my summation rule. N times n plus 1 over 2. And then once everything's in terms of n, then I can have an easier time evaluating my limit. Okay, everybody okay so far? Okay, let's expand all this out so that we can have a clear picture as to what the numerator and denominator is going to look like. Okay, so now things are much more clear, right? What's my limit gonna be? Just 2, right? My degrees are the same. So I'm just gonna look at my leading coefficients. 4/2 is equal to 2. All right, so this is the process that we're going to have to be comfortable with before we're because we're kind of starting small, we're building this out into something that is going to be helpful tomorrow and Friday. So if you look at example 7, there's even more expansion that we have to do, right? We got to expand everything out, split up into individual terms, take care of all the n's, and then or take care of all the i's, convert everything in terms of n, and then we can do the limit of each piece separately. We're kind of applying what we need to get to, building it up little by little. Okay, so let's look at example 7. So just like how we did example 6, we're gonna have to clean up our i's before we can get to our n's, but we have to do something beforehand. We gotta expand all this out, distribute this through, and then at the very end, we can take care of the limit. Okay, so first things first, I'm gonna FOIL this out, get that 1 plus 2i over n, expand it out, and then I can worry about that 2 over n, distributing that through. So first, I'm just going to bring that 2 over n out in front. So just I'll expand this out once I take care of this piece here. Oops, sorry, that 1 is separated. I'm going to FOIL this out first. And then once I fold this out, I'll distribute the 2 over n through. So I'm just trying to separate all that mess to begin with. So 1 times 1, 1 plus 2i over n, 2i over n times 1, 2i over n times 2i over n. Combine my like terms in the middle. Okay, distribute the 2 over n through. There's a summation that needs to be applied for each of these. So I'm going to start separating them out, and then I'm going to pull my coefficients out in front so I can isolate my summation 1 for my summation I for my summation I squared. So one step before I go through that. Anything that's not part of my rule, I can just push it out in front. So I now should be able to find the clean substitution for all these pieces from the previous page. So 2 over n times, summation 1 can be replaced with what? N plus now these are 3 separate terms, so I can apply the limit to each of these fractions independently. Now, these two, they don't look too hard to expand. This one looks like a mess, right? I have to expand all this out before I can get to my limit. But do we care about every term when we do limit as n approaching infinity? We only care about the what? The highest degree, right? Anything that's a lower degree just washes out. So the shortcut here is we don't have to FOIL everything out. We just have to FOIL the part that's going to give us that highest exponent. So now these two is not too bad, right? We're not going to have to worry about this. But when we get to this part here, we only have to worry about the 8, the n, and the 2n, right? There's more to it than that, but we know those pieces will give us the highest exponent along with the highest degree, along with the coefficient. Everything else is just going to be a lower degree. It's not going to even matter if we're doing limits as n approaching infinity. Okay, so what's 8 times n plus 2n? 16n to the what? Third. Now, there are more terms after that, but it doesn't really matter, right? Because we have what we need. Do all the degrees within each fraction match? And it should. Okay, so that's when we know we're on the right track. Okay. Later on, we're going to have to deal with a problem that's going to extend beyond or before this. But when we get to this point, we're looking at each of these fractions. They should all give us matching degrees. So the first term will give us what? 2, right? 2 over 1 with degrees match. Just take my coefficient. My second fraction will give me what? 8 over 2, which is 4, right? The lower degree doesn't mean anything. It's just the highest degree. In my third term, there's an n squared, an n, and a constant, but we already have what we need, so we need to ignore the rest. 16 over 6. The limit as n approaching infinity will be 3 terms, and we add those together, 2 plus 4 plus 8/3. Gives us 26 over 3. So we're just building the foundation that we need for the big picture that we're going to talk about tomorrow and Friday. Okay. Okay, you guys have homework from 4.2. It's in your homework packet. Okay, come up and get your phones.